Okay, so let me do the exercise with the ChatGPT for problem set 11. To access that, I'll need to clear these requirements. And actually, I think I can take the last one and then click next. So this, and from here, now click next. And this is a small problem set. This used to be done during the Thanksgiving week. That's what was one of the reasons it had only 5 problem sets. Now the reason it has only 5 questions is because this is the week where you also have to look back at the past ones and do DC circuit. So so I might actually do DC circuit today. Let's see what kind of questions we get here, and then we might do DC circuit. Let me have ChatGPT answer this. I confuse myself with this setup all the time. Let's see if ChatGPT can get this right. Let me first paste in my message involving inductors. Inductors in a yeah, and it's so let me give ChatGPT full explanation. So I'll paste this in and I'll say, my professor is saying he confuses the directions himself with this question. So I think he is no help. Can you help me? Let's see. Can I get the correct answer this time? So the way I like to think about inductors is that inductors oppose change in current. So in A, it is increasing, and this is also increasing. All right. This is randomized, by the way. I think there's 4 possible versions of this question. So if the current here is increasing, then inductor will do things that's gonna produce a voltage opposing it. So I think voltage on the right end should be higher, and here the left hand should. That's what I would guess. I don't know if it's right. Look at ChatGPT's answer. Higher potential in the current is increasing. Changes in current. I think that actually means is this end high? I think, okay, I'm gonna switch my answer. This changing current. That's right. Where the increases the inductive loss on EMF. This is one of the. By the way, with the circuits problem solving, you can almost ignore the electromagnetic underpinnings of the circuits. You can just treat it like a math problem. This would be the starting point in that approach. Whenever you see inductor, you see them as governed by this formula without really paying attention to what does V mean, what does L mean, what does I mean. You can almost treat it like a math problem. And, depending on the setting, that might actually even be recommendable. So, anyways, all that current is increasing in the direction shown. According to the rule, inductor will make the left side higher potential to okay. RP increasing offensive direction, right side okay. So my changed answer matches ChatGPT's answer, and I swear I didn't look ahead to what it was saying, and I don't know. Now the challenge is that I programmed this in. So, when this is wrong, is it wrong because I was wrong when I was programming in, or am I being wrong now? So I think if I were to justify it, this is how I would justify it. So if you have constant current flowing through the inductor, assuming it's like superconducting, no voltage difference between either end. So I think I'm looking at, rather than induce the voltage, I'm looking at what's causing the current through the inductor to increase. And in order to make the current through the inductor increase, this end has to have a higher potential, in the sense that if you took a voltmeter and measured it across, then this would be higher end. At some point, I just have to do this thing in the lab, because again, I confused myself. And so let me just paste this in and ask ChatGPT. It looks like the opposite is the case. Is there an error in the question? Maybe. uh, no, that's not quite right. Um, I don't know. That's so confusing. All right, let me do this. I think not during this session, but I think I might just record myself setting this up experimentally and just making measurements experimentally. Let's do it that way. That way, whether I'm confused or not has no bearing, and I'll just do that. But yeah, so yeah, again, this is the. Figure 14.8. Maybe that does actually give the correct answer. Let's look. So I just don't trust my own reasoning process. So I'll just trust the textbook's reasoning process. So textbook says, yeah, this one matches to left hand, higher voltage, like battery here. And yeah, so once you sign for this is right, then the rest I think I can get. Yeah, so I mean these answers are consistent with the figure 14.b. And what I will do is I'll just build this circuit quickly in the lab, and then I'll just record me doing that little experiment and just confirm that yes, these answers are correct. But for better or worse, in this particular setting, ChatGPT is as good as I am or as bad as I am, because both ChatGPT and I had it wrong first. Yeah. This is the kind of thing where when you're dealing with the circuits, you don't really worry about getting the sign right, because you do the analysis, and if you got the sign wrong, just reverse the directions. You just measure stuff, and that habit of sloppiness is coming back to bite me. All right, let's. I think that's probably all the time we have for problem set 11, and it's a short set. And this is circuit analysis. I don't know if I've ever done it, so let me. Nah, it's fine. I think there's probably gonna be more interesting questions to ask in problem set 12. So let me go do that instead. And as promised, here is a measurement with an actual circuit. We have the inductor in series with a resistor. One side of the resistor serves as ground, and the voltage measured on the other side is proportional to the current. The function generator applies a triangular wave to the circuit, and the oscilloscope displays the voltage at 2 points in the circuit. Channel B displays the triangular wave applied across the resistor and inductor. Channel A, the rounded curves, is proportional to the current. It also displays the voltage between the resistor and the inductor. So at points where the triangular wave is higher, there is a voltage drop as the current crosses the inductor. And at points where the triangular wave is lower, there is a voltage rise as the current goes through the inductor. And you can see that at points where the current is not changing, the voltage across the inductor is 0. You can see that at points where the current is decreasing, there's a voltage rise as the current goes through the inductor. And at points where the current is increasing, you can see that there's a voltage drop as the current goes through the inductor. So that's the experimental answer. Again, the rounded curve shows the voltage drop across the resistor, which is proportional to the current. And at places where the current is increasing, the voltage drop across the resistor has to add up to the voltage drop across the inductor to equal the output signal. So in those places, the voltage drops as the current goes through the inductor.